Hello everyone. This is going to be a tutorial on how to use analog behavioral modeling using Cadence PSpice version 16.6, and my name is Armando Pardave. And before we get to examples on how to use this advanced analysis for PSpice, I want to go over the definitions. So what is behavioral modeling? It is a process of developing a model for a system from the viewpoint of externally observed behavior rather than from a microscopic description. In other words, we're going to be working with blocks in which only the importance is the input and output or the transfer function. So how is this different from other types of modeling? Almost all the simulations we've done in PSpice so far have used what's called structural modeling, in which we use the capacitors, resistors, inductors, and chips. We try to model the actual hardware of it, but sometimes we just care about the input output of the transfer function of the model, and not so much of what goes inside of it, all the components, all the attributes, and such things. Here I have a non-inverting amplifier with a gain of 8. Now I have built the amplifier and all the circuitry around it. But what if I want to replace all this by a single block that will take the input and amplifies it by 8? In other words, it will times it by 8 directly without putting all these components. Well, that is possible if I use the ABM library or the analog library. They both carry a gain block. I set the gain to be 8 this time. So the actual schematic with all the components and the schematic with only the block will give me the same result. Here I have the output waveforms. So if we just care about the input-output relationship, we can use a block. I have also used a signal differentiator in another example. So here we have the input-output waveforms of a differentiator, and whenever the input has a positive slope, our output is positive because it's taking the derivative, and whenever the input has a negative slope, then the output goes below 0. So this is just an example of a block. This is the differentiator block that we're using. So let's look at the first example. Let's say I have a system in which I want the input to be the time and the output to be that time plus 1, everything raised to the power of 3. How am I going to do this? Well, let's go to the schematic. I have an empty schematic here, and the first thing I'm going to do is locate the ABM library, which I have right here. Okay, so my input has to be the time, so I select the first function, which is ABM, and ABM comes with a value of pi as a default, but I'm going to change that to time. Okay, there we go. It should be noted that if I double click on the block, I have a space for more expressions, not only time or a constant, but more expressions. So it's not just limited to what I have right now. Okay, so that's my input time. What's next? From the same library, ABM, I'm going to call eValue. Okay, but why eValue? So what eValue does is it outputs an expression in terms of the input. So what I'm trying to say is it's going to take the input voltage difference, then you can write the output in terms of that voltage. So this expression right here is the input voltage, the difference between the positive side of the input and the negative side of the input. So that's our Vin. So I'm going to add 1 to it. And then what else do I need? What I need is to raise it to the power of 3. Okay, so I'm going to call another function which is power, PWR, the expression, comma 3. Now why comma 3? Because I'm raising to the power of 3. So that represents the exponent. Hit enter, and I have the expression right here, which is the input voltage plus 1 and everything raised to the power of 3. Okay, great. So I'm going to need a load to test this out. Now what happened is that since I don't have the analog library selected, which the resistor belongs to, it just asked me if I still want the resistor, which I do. So I just say yes. Alright, so that's my resistor. I'm going to need a couple of grounds. So I have a ground here for the negative side of the input, a ground for the negative side of the output, and for the load. And now let's make the connections. So everything from here should be your standard connections. Great. Alright, so we're done with that part. Just gonna put a voltage probe here in the to look at the input. On PSpice, we click on edit simulation profile. Okay, so I have it set up to 6 seconds on the time domain. Okay, so let's run it and see how this looks like. So we run this, open it, and this is what we expect for the input. That's the input right here, the time matching the voltage in the input. Okay, so when the time equals 3 seconds, the input voltage is 3 volts. 4 seconds, 4 volts. Okay, this is just the input again, it's not the output, so the value hasn't been added 1 and raised to the power 3. Now let's look at that. So what I'm going to do is add another plot, okay, to show the output. Let me clean the grid to have a better view of the lines. And then I'm going to add the output. Okay, so that looks better. So let's have the output right here. Trace, add the trace, and right here, this is the output as after it has been added a value of 1 and raised to the power of 3. So, and as we expect, we get a third-degree line equation. Okay, so how do we know if this is right? Well, let's try a point. So if we go back to the equation, let's say t equals 4. So when t equals 4, this will be 4 plus 1, that's 5. 5 to the third power, that's going to be 125. So let's see if this is consistent. Okay, so we hit here to follow the trace, and at t equals 4, about right here, let's see if it's close to 125. If we see right here, it says 125.021. That's good enough. Okay, we're just trying to see, probably because the cursor is not sitting exactly at 4. It's not giving you 125 exactly. Okay, so we expect some error there, but that's good enough, sufficient enough to see that it's working. Okay, great. So what else? Now let's say that I want this function to be integrated over some time interval right here. So the same function that I had before, I'm going to integrate this from 0 to 5. So from time equals 0 and then up to t equals 5. I already have solve the equation or the integral, which the result is 323.25. I'm not making this up. This is something I grabbed from Wolfram Alpha. Okay, it's right here. So how can we do this in the circuit? Oh well, let's first have some space for the integrator. Let's move the load to make up for that space. In the same library, ABM, okay, we're going to find the integrator right here. We select it. There we go. And we make the connections. Okay, great. Let me just change the probe. So I'm gonna have one before it gets integrated and after it gets integrated. Okay, so let's run it. See what we get. Okay, great. So the green line is the third-degree equation and the red line is the integral of it as a function of time. So let me clean this again. I want it to look neat. Okay. Okay, so what did we say was the value, numerical value from 0 to 5? It was 323.75. So let's see if that's correct. Now we go back to the schematic, or the output, I will say, and let's trace it. So of the value here. Here's the output. So at t equals 5, it should be around 323. Around there. 323.813. Again, close enough. That is sufficient. And so it does work. Okay. Now, going back to the schematic, you have more functions in the same library. You can take the derivative too, which is defer. That's the function that will take the derivative, and you have more other functions that you can use to model a system. Okay, for a second example, I'm going to have a bandpass filter. So I'm going to use the ABM library again. Okay, and I have here the low pass filter. Gonna input that in here, and as an input I'm gonna have a sine function. So v sine, yes, I'm gonna accept that because I didn't have the actual library selected. That's fine. And let's have a load R. Okay, so first, before I do the bandpass filter, I'm just going to do a low pass and then cascade this with a high pass filter. So let's put a ground. For the input and for the load. Let's make the connections. Okay, great. All right. So V off, it's going to be 0. The amplitude, let's just put 1 volt. Frequency 1K. AC, we're going to do a AC sweep. So let's put this 1 volt. Alright, so we're all set. Let's go to PSpice, edit simulation, and we're going to change from time domain to AC sweep. Okay, start frequency, let's put 1, and frequency, well, let's see, let's put 10K for now. Points per decade, 100 points per decade. That should work fine. And let's see what the output is. So let's run it. And then we're going to adjust that as we so that's the low pass filter. We see this spike right here because the attenuation is a little bit big. So let's change this 1 dB to maybe 0.01 dB. Now let's run it again, see if it gets better. It should get better. All right, great. So there we have it. Okay, low pass filter. Let's now add a high pass filter, but let's see. Let me just shift this low pass filter so you have a attention 1K. On this one at 10K. Let me also change the simulation profile to have it up to 100K. Let's see, let's run it now. All right, here's my low pass filter. Okay, so filtering up to around 1 kilohertz, all those frequencies. Now let me put this in series or cascade with a high pass filter. Okay. So on the AVM library again. Now high pass filter, high pass right here. I put in series with it. Make the connection. Okay, great. Let's put this one to 0.01 dB, so we don't have that big spike. Okay. So 10 hertz. Okay, so let's run this, see how it looks like. All right, great. So we have right here a band pass filter. It's pretty much what I did is a low pass filter with a high pass filter, and so it's just accepting from 100 hertz to up to 1K. Okay, the bandwidth right there. Now it should be noted that we could have done this with a band pass. There is a function that will do what these two do with a single block, but I just wanted to show you whether if you wanted just a low pass filter, high pass filter, or just cascade those two. So okay, let's look at the third example. And what I'm going to try to do here is rectify a sine wave function. So first let's grab the v sine function. Put it right here. Let's set v off to be 0. Amplitude, I'm going to put 10 volts for that, and frequency is frequency of 1. Okay, AC, even though we're not going to need it, I'll just put the same as the V amplitude. And I'm going to the ABM library and call eValue. Right here, we used this before. Okay, let me put a load. And all right, so let's make the connections. I'm gonna need a couple grounds. For the negative sides of the input output, the load, and the sine wave. So let's make the connections. Okay. All right. So how we're going to do this? Well, in the expression, we're just going to have the absolute value of it. ABS okay. Let's edit the simulation profile. Up to 5 seconds, that's good enough. The frequency is 1. So you can see about 5 periods. And put the input of probe, voltage probe here, input and output, so we can look at both. Let's run it. Okay, great. So as we can see, the red line is the output, the input being rectified. Let's delete the input for now. We can only see the output right now, so it's the output being rectified. So it's taking the absolute value of the input. Okay, so on top of that, I want to add something else. I want to show you the usage of if statements, which you can do with eValue as well. Okay, so what I'm going to do is modify this file, and let's say every time I'm going over 5 volts, I want the output to be 5, but if it gets below 5, I want the output to be 0. Okay, so how am I going to do that? Well, how can I write an if statement? We can click on the expression, and I'm gonna type the if statement. If the absolute value of the input it's greater than 5, then we're going to output 5, else output 0. Okay, so let's see. Let's run again the file. See how it works. All right, great. So there we see the square waves. Okay, every time the input is going above 5, the output is being 5. Then when it falls below 5, it goes down to 0. Okay, so that's one of the usage for the eValue box, the if statement. So let's look at this example right here. I already have built the circuit, and what I have here is a sine wave and a square wave. Both have a period of 1. So you can see here the frequency of 1. This is the period of 1. They oscillate between positive 10 and negative 10. Let me show you the output already here. That's the output. So the square wave and then the sine wave. So what I'm going to show you is I'm going to add these two signals right here. This block, you can find it in ABM sum. Okay, and after we do that, let's see what we get. So let me change the probe to the output right here. Let's see what we get. So we get this wave right here. Alright, which is actually just addition of the two waves. Now I also added a gain of 10, so it's gonna be multiplied by 10. The output, so far we have it up to 20 down to 20, so if we multiply by 10 it should give you 200. This block right here, you can find it in the same ABM library. It's called gain right here, gain. So you can set the gain to any value you want. So 10 for this one. So if we change the voltage probe, it should go between positive 200 negative 200, which is what happened here. Okay, in the green output. So that's what we expected. Again, the ABM library has unlimited ways you can define a system. You have if statements, you can model it adding, subtracting, multiplying different signals. You can also make independent sources, but there's so many different, it has a lot of capabilities. So you should explore those and make your system, model your system depending on what your input output is. Thank you.